Section 3.4, Absolute Value Equations and Inequalities. Our goals for this section are to solve absolute value equations algebraically and graphically, solve absolute value inequalities algebraically and graphically, and then we'll look at an application involving an absolute value inequality. Alright, so let's get a basic idea of an absolute value equation. Let's consider the statement absolute value of x is equal to 5. And we might just sort of think, well, how many solutions does it have? And just by inspection, we can see that this equation has two solutions. Specifically, we know that if x was negative 5, its absolute value is 5. And if x is positive 5, its absolute value is 5. And we can see that graphically as well. On this graph, here we have graphed the function y equals the absolute value of x. And I can see that if I were to draw the horizontal line at y equals 5, I see that it has two intersections. Here's 1, and here's 2, and those correspond to when x is negative 5 and when x is positive 5. So again, we see two solutions, and again, they are x equals negative 5 and x equals positive 5. Now, what if we had the statement absolute x equals 0? Well, let's look at that statement and thinking of it in orange. If I were to graph y equals 0, that's the horizontal axis, and notice that there's only one intersection, and that's specifically when x equals 0. And what if we had the statement absolute value of x equals negative 3? Well, graphing y equals negative 3, notice that the absolute value function does not intersect y equals negative 3 at all. And so this statement has no solutions. And these ideas can be clarified and generalized. So in general, if x represents an algebraic expression and a is positive, then the absolute value of x equals a will have two solutions, x equals a or x equals negative a. If a is equal to 0, then absolute value of x equals a will only have the one solution at x equals 0. And if a is less than 0, then absolute value of a will have no solution. And these are the same ideas we just saw using that graph. Alright, so let's consider the equation. Absolute value of 3x minus 4 is equal to 5. So since we have an absolute value, an expression involving this absolute value equal to 5, we can break this up into two equations. We can say 3x minus 4 is negative 5, or 3x minus 4 is positive 5. And now we will solve each of those equations. So to solve for x in the first equation, I would add 4, yielding 3x is negative 1, and divide by 3, so x is negative 1/3. In the second equation, I would add 4, yielding 3x is equal to 9, and dividing by 3, x is equal to 3. And the equation has two solutions. Let's look at the second equation on this slide. We have 8 times the absolute value of negative x minus 12, subtract 2, is equal to 22. The first thing that we need to do is isolate this absolute value expression. And so to do that, we will first add 2. So we have 8 times the absolute value of negative x minus 12 is equal to 24. and then we will divide through by 8, yielding the absolute value of negative x minus 12 is equal to 3. Now we can break this up into two equations. Negative x subtract 12 is negative 3, or negative x subtract 12 is positive 3, and we'll solve each of these equations. Adding 12 on the first equation yields negative x is equal to 9, and then changing signs, x is negative 9. Adding 12 to both sides on the second equation, negative x is 15. Changing signs, x is negative 15. And so again, two solutions to this equation. So now we have the equation absolute value of 9x minus 6 is equal to the absolute value of 4 minus 3x. Well, this is kind of tricky. What do we do with this when we have two absolute values? Well, let's think of it first in simpler terms. What if we had just the absolute value of A is equal to the absolute value of B? Let's just think of that. How could we find solutions for this? Well, for this to be true, it's certainly true if they're equal. If A is equal to B, we get a solution. How else could we get a solution? And the other way to get a solution would be if they were opposites. If A was equal to negative B. If we have either of those situations, if the two sides under the absolute values are equal, or if they are opposites, we get a solution. So we can apply that to this equation. We have the absolute value of 9x minus 6 is equal to the absolute value of 4 minus 3x. So then this is true, this will be true if one of the following situations is true. 9x minus 6 is equal to 4 minus 3x. A is equal to B. It could also be true if they are opposites. So if 9x minus 6 is equal to the opposite of 4 minus 3x. And now we solve each of these equations. Alright, so for the first equation, I will add 3x to both sides. That gives me 12x minus 6 is 4. Adding 6 to both sides, 12x is 10. Dividing through by 12, x is 10 over 12, which is 5 over 6. So there's one solution for the equation. Now what if they are opposites? Well, first let me distribute on the right-hand side. 9x minus 6 is negative 4 plus 3x. And now I'll subtract 3x from both sides. Yielding 6x minus 6 is negative 4. I'll add 6 to both sides. 6x is 2, and I'll divide through by 6, and x is 1/3. So we get two solutions to the equation. X is 5/6, x is 1/3. So now let's consider absolute value inequalities. This graph shows y equals the absolute value of x minus 2 in blue and y equals 5 in red. And we'll use the graph to solve each of these statements. Where is the absolute value of x minus 2 equal to 5? Well, we see we have these points, these boundary points, where, let's see, x is negative 3 and x equals 7. So negative 3 and 7 are the solutions, and you could write that as, x equals negative 3, x equals 7. And now thinking about how we thought of inequalities in a previous section, I'm going to kind of draw some boundary lines here at negative 3 and at 7. Boundaries. So now the corresponding inequalities will be bounded by those lines. Alright, so now in purple, I will consider where is the absolute value of x minus 2 less than 5. And I see that all of these points, all of these outputs for the absolute value of x minus 2, all of these outputs are less than 5. And so smashing those points to the x-axis, I get this interval. And the interval goes from -3 to +7. And so I would write this as the interval -3 to 7. I'll consider the last statement in orange. Where is the absolute value of x minus 2 greater than 5? All right, so finding the points on that blue curve that have outputs greater than 5, well, we'd have these points and these points all have y values greater than 5. Smashing those points to the x-axis, I get this interval and this interval. And notice again that they're bounded by those black lines at x equals -3 and x equals 7. So the solutions to that inequality, x minus 2 is greater than 5, would be the interval -infinity to -3 union 7 to infinity. So now that's how we would solve those, how we would write the solutions with interval notation, but we've also talked about how we could write solutions involving just inequalities. So I had the statement -3 to 7 as the solution for that first inequality, but I could also write that as x is between -3 and +7. So we get that three-part inequality. For the second, for that last inequality, absolute value of x minus 2 is greater than 5, I could have written that as x is less than -3 or x is greater than 7. Alright, so I'm doing that because in the next slide we're going to see similar statements as to those inequalities I just wrote. So in solving absolute value inequalities, in general, if x represents an algebraic expression and a is positive, then the absolute value of x is less than a is equivalent to writing -a is less than x is less than a. And the absolute value of x is greater than a is equivalent to writing x is less than -a or x is greater than a. And the same principles will apply if we replace those less than or greater thans with less than or equal to or greater than or equal to. Alright, so let's consider an example. We have the absolute value of 2x plus 9 is less than or equal to 2. Since this is a less than inequality, what I can do is I can bound the 2x plus 9 on either side with 2 or its opposite. And now I can solve this inequality. I'll subtract 9 from all parts. So then -11 is less than or equal to 2x is less than or equal to -7. And I'll divide all parts by 2. So then a -11 halves is less than or equal to x is less than or equal to -7 halves. Now we're asked to graph the solution set. All right, so since we're bounded by -11 over 2, that's -5.5, if you want to think of it in a decimal. And -7 over 2 is -3.5. And so what we could do is draw the interval from -5.5 to -3.5 and shade in between. And I used brackets because those are or equal to's. Now if we wanted an interval notation for this, the interval notation would be bracket -5.5, comma -3.5, close bracket. Alright, let's look at the other example. We have the absolute value of -3x plus 5 is greater than 8. Since this is a greater than inequality, I can rewrite this as two inequalities. Negative 3x plus 5 is less than negative 8, or negative 3x plus 5 is greater than 8, and solve each of these inequalities. Alright, so for the first inequality, I will subtract 5. So then negative 3x is less than negative 13, and I'll divide by negative 3, so x is greater than 13/3. Remember, whenever we divide both sides of an inequality by a negative number, we must flip the symbol of inequality. Alright, for the second inequality, I will again subtract 5, so then negative 3x is greater than 3, and I'll divide through by negative 3, so x is less than negative 1. Alright, let's graph this on the number line. X is greater than 13/3. 13/3 is, what, 4 1/3. So 13/3, and we want x is greater than, so we'll put a parenthesis at 4 1/3, and I will shade to its right. X is less than negative 1, a parenthesis opening to the left at negative 1, and shading to the left. And there's the graph representing the solution. And we should, of course, have the or here between these. So here's the solution symbolically using inequality notation. There's the symbol, there's the solution graphically on the number line. And if we wanted interval notation, negative infinity, comma, negative 1, union, 13/3, comma, infinity. Alright, let's look at a couple more. 2 times the absolute value of 4 plus 6x is greater than or equal to 8. So then dividing through by 2. Let's divide through by 2 to isolate the absolute value. Then we have the absolute value of 4 plus 6x is greater than or equal to 4. And now we'll break this up into two inequalities. 4 plus 6x is less than or equal to negative 4, or 4 plus 6x is greater than or equal to 4. On the first inequality, subtracting 4, we have 6x is less than or equal to negative 8, and dividing through by 6, x is less than or equal to negative 4/3. Or, for the second inequality, subtracting 4, 6x is greater than or equal to 0. Dividing through by 6, x is greater than or equal to 0. Let's graph that. See, x is less than or equal to negative 4/3. 4/3 is 1 1/3. So I'd put a bracket at negative 1 1/3, and I'll shade to the left. And I'll put a bracket at x equals 0 and shade to the right. The interval notation would be parenthesis, negative infinity, comma, negative 4/3, bracket, union, bracket, 0, comma, infinity. One plus 4 times the absolute value of x minus 4 is less than 9. Again, we will first isolate the absolute value. I'll subtract 1 from both sides. 4 times the absolute value of x minus 4 is less than 8. I'll divide through by 4. And the absolute value of x minus 4 is less than 2. Now I'll turn this into a three-part inequality. Since we have a less than inequality here with the absolute value, I will have the x minus 4 bounded on either side by negative 2 and 2. And now to solve for x, we'll just add 4 to all three parts, yielding 2 is less than x is less than 6. And so to draw this on the number line, a parenthesis at 2, a parenthesis at 6, shaded in between, and if we want the interval notation, parenthesis 2, comma, 6, close parenthesis. All right, we'll finish off this section with an application. We're told that a machine in a production plant fills bottles with 20 ounces of corn syrup. The machine is designed with a tolerance of 0.2 ounces. So here we're talking about tolerance. Well, that means that the actual amount in the actual amount that the machine fills the bottle with is going to be close to 20, but it can deviate from 20 by up to 0.2 ounces. We're asked to write an absolute value inequality that expresses the amount of corn syrup that could end up in the bottle. All right, so the actual amount in there is going to be close to 20. So let's call x the actual amount. Well, what we know is that if we take the difference of the actual amount and 20, it should be close to 0.2. That's what the tolerance is. Okay, but wait a second. It could be greater than 0 or less than 0. So what we do is we put an absolute value, and we say that under absolute value, that tolerance is 0.2. All right, so the absolute value of x minus 20 is less than or equal to 0.2. All right, so now we're asked to solve the inequality and interpret the answer. All right, so the absolute value of x minus 20 is less than or equal to 0.2. So then negative 0.2 is less than or equal to x minus 20 is less than or equal to 0.2. And we'll add 20 to all three parts of the inequality. So then 19.8 is less than or equal to x is less than or equal to 20.2. Interpret the answer. The actual amount of corn syrup in a bottle can be as low as 19.8 ounces or as high as 20.2 ounces. So it's going to be somewhere between 19.8 and 20.2 ounces. All right, that concludes the presentation for section 3.4.